Good morning. First of all, I would like to thank the organizing committee for inviting me to participate in the fourth annual Congress on Plant Science and Biosecurity. Therefore, I'm going to start with my presentation entitled Degraded limonoids, biologically active limonoid fragments, re-enhancing interest in Meliaceae and Rutaceae sources. Well, I would like all of you move away from a myth which relates the term degraded. Why? Because quickly a degraded compound is associated with a cheapened, devalued, or deteriorated compound. That is the reason why I prefer to talk about limonoid fragments and rather than degraded limonoids. And in this way, degraded limonoid is not only a product of bond cleavage and loss of functional groups from an original limonoid, but these compounds represent a natural underexplored chemical space, which of course offer possibilities to find new biologically active molecules. In 1997, Okamura and co-workers reported that only 5 naturally occurring degraded limonoids were known. They were isolated from Meliaceae and Rutaceae plant families. However, although rating was missed in this review, possibly because in the 60s and in the 70s, uh, mm, a degraded the same name, odoratin, was given to two different metabolites, degraded limonoid and a sesquiterpene lactone. And this could be the reason to explain that confusion. Years later, flavonoid was named odoratin as well. Therefore, it could be advisable to use alternative names for these three molecules to avoid error. Sorry. The number of isolated degraded limonoids has increased significantly in recent years, and it is true that the chief sources of limonoids are the Meliaceae and Rutaceae plant families, but they also can be found occasionally in other plant families. This can be attributed to the improvement of the NMR equipments, which led to characterize minor natural products that they were undescribed previously. But nevertheless, the role of these natural products in roots, twigs, and leaves remain unclear. We could speculate that they are the result of the microbial decomposition of limonoids, or even they could appear when the plant is attacked by insects, fungi, for example, showing us the chemical potential of plants to defend themselves. Regarding today chemical structures, we can classify degraded limonoids in two groups: highly and slightly degraded limonoids, depending on the degree of degradation. I mean, if they have lost just one ring or several rings from the precursor. Most of the highly degraded limonoids are characterized by a fused bicyclic substituted lactone with a 13-alpha methyl and a 17-alpha furyl group at the ring junction position, which could come from the C and D rings from the precursor limonoids. Based on the motif of the large motif size present in their structures, we divide them in two groups as well. Limonoids bearing a delta Valero or a gamma butyrolactone ring as a B ring. In the first highly degraded group, 23 natural products are included presenting this valerolactone. Sorry. Most of the absolute configuration on the carbon 13 and the carbon 17 for these molecules were described with alpha-oriented furyl and methyl groups. Curiously, the alpha-oriented furyl and methyl groups in most of dictandiol derivatives were based on biosynthetic assumptions. But in spite of the limonoid precursors isolated today, Fischer both groups oriented to the alpha phase, Zhao and co-workers assigned the absolute configuration for dictandiol as beta 17 furyl, beta 13 methyl using crystal X rate diffraction. Similarly, beta 13 methyl and beta 17 furyl configurations were established for isodictandiol and dictandiol A. Due to the total synthesis of these compounds has not been described in literature yet, the preparation could shed light on these stereochemical discrepancies. Besides, 19 compounds have been isolated containing the butyrolactone ring. Noting that the numbering of carbon atoms to describe the structure of degraded limonoids can sometimes be confusing due to the lack of consensus among authors. Many authors prefer to keep the original numbering corresponding to the intact limonoids, while others use the carbon atom numbering of the degraded limonoids themselves. Due to these numbering discrepancies, some structures have been named in different ways depending on the numbering criterion chosen. This is the case of daisy carbon, which was wrongly described as a new metabolite in 2002, when really it was described 5 years ago by Zhao and co-workers. Until date, only 7 of these metabolites are considered as slightly degraded limonoids. They are the ones I show on the screen. Naturally occurring bioactive agents, including limonoids, were gaining popularity over synthetic compounds in issues such as anti-inflammatory processes or preventing and even treating cancer. Nowadays, we also know that some of the fragments are active as well, in spite of largely their biological properties remain poorly known. They could reveal the active core of limonoids. Sorry. So, the bioactivities shown in diverse biological processes could open a promising future in terms of development of new active molecules, which could be quite useful not only in the agrochemical area, but also in the medical area. Here we have fraxinolone, This is the most studied degraded limonoid, and it resulted to be active in a wide variety of biological assays listed on the screen. Papers have recently published, and many scientists thought this compound could protect the plant from attacks by certain insects. But what is even more remarkable is the biological processes in which it plays a role connecting with the field of medicine, and it could be a promising lead compound for the treatment of some diseases, including cancer or anti-inflammatory disorders. For most of them, the biological properties of degraded limonoids have not been described yet. However, some of them have been tested as pesticides and potential drugs. Here we can see that scientists focus their attention in the insect controlling test, but nowadays we also know that around the 23% of them exhibit interesting anti-inflammatory activities, which is also quite interesting. But in addition, it has been shown that they are also active molecules in many other processes, like the ones I show on the screen. In spite, it is not clear at all if the deconstruction of limonoids is promoted by the young plant or by microbial systems. Their origins have been postulated in some reports searching for plausible intermediates in this conversion. For instance, in 1979, fraxinenolone was hypothesized to be formed through decomposition of limonene, whereas a few years later, calodendrolide was hypothesized to be the precursor of fraxinenolone as well. But, sorry, this is really a bit difficult to see. To my point, this is unlikely if we consider that calodendrolide, the possible precursor, has not been isolated or even detected in low concentration in other plant families apart from Miliaceae. Some other researchers have tried to explain the degradation through three hypothetic intermediates to explain how a few of these degraded limonoids could be obtained. Others have tried to make hypotheses by proposing some plausible transformations, but in most cases, very poorly detailed theoretical approaches have been made. Despite their low structural complexity, very few syntheses have been described in literature for these fascinating carbon scaffolds. In fact, in 2011, Heasley published an excellent review on progress made in limonoid synthesis, including degraded limonoids. At the time, only the total formal synthesis had been performed on these six degraded limonoids. Later, only the preparation of an hydroxylated derivative of fraxinenolone and milazoline B were described. To the best of my knowledge, no total synthesis or semi-synthesis of the remainder degraded limonoids has been performed. So, and most degraded limonoids were not synthesized yet, it should be quite interesting to carry out the preparation of them, and at the same time we could shed light on some stereochemical discrepancies. Only a numerous set of chemical transformation using fraxinolone as a substrate were carried out. These derivatives were mainly studied as insecticidal agents against lepidopteran insect pests. And here we have some derivatives where the A or B rings were modified to introduce esters, hydrazones, ester of fraxinolone in the carbon 9 and carbon 30 oxime position, and some phenylpyrazones. Regarding the serine, halogenation and acylation reactions were carried out as well as some carboxamide and 1,3,4-oxadiazole were connected to the furyl ring. On the other hand, a few biotransformations have been reported, and in all of them, Aspergillus niger was the microorganism in charge of these transformations. To conclude, I would like to highlight these three ideas. We have now a deep knowledge about how the degradation of limonoids and why the degradation is carried out, but which is also more important, many of these compounds have not been tested yet, in spite of the good results obtained with fraxinolone and others. We anticipate that these metabolites and their analogues could be used in the designing of new agrochemicals and therapeutic agents. If you are interested to know some more about degraded limonoids, I would recommend to read this publication, or if you like, you can contact me. Sorry. So, thank you all for your kind attention.